So just something that I want to note is that thanks Isaac for helping me out with this. The hotspot names for each of the robots has been updated. So now you'll see ROS master and then whatever the number of the robot is. So hopefully this will help if multiple of you are using the same robot, that you won't have the confusion of what hotspot you're actually connecting to. So if you have any problems with that, please let me know. I'll also reiterate again that robot 6 has significant drift. And so I contacted the company, and hopefully after their Lunar New Year celebration, they'll get back to me with some possible suggestions as to what's going on with that particular robot. But all of the rest have been working well. If you do have any problems or notice anything, then please let me know so I can get in contact with the company as soon as possible. The 12-hour delay time difference does make a huge difference as far as how long it takes me to fix any problems that arise. So last time we left off talking about the different mobile robot car kinematics, and what we'll look at today is the setup that's like the robot that we're using. So just as a reminder for what we talked about last time, is that there are two wheel types for the Mecanum wheels. So the Mecanum wheels are a specific case of the Swedish wheels. So those are wheels that have rollers on the outside perimeter of a standard wheel. And the Mecanum wheels have those rollers at an offset of 45 degrees from the wheel plane. And so we have the first type, which is the A wheel, or L on the ROS master. And so the rollers are angled in this way if we look at it from the top. And if we apply a forward rotational velocity to the wheel, the actual velocity will be, so if we apply forward velocity, the actual velocity is forward and right. And so if we apply backward velocity, that would be backward and left. And then we have the B wheel. So this is where we have from the top view that the rollers are in the opposite direction from the A wheel. And in this case, if we apply a forward velocity, then we get forward left motion. So apply forward velocity. Our actual velocity is forward and left. And so when we have a mobile base and we want to have 4 wheels, the typical configuration and what we have for our robot that we're using for the project so what we have is the wheel in the front left side is an A type, and then the other A goes in the diagonal, and we put B's in the other two. So So this is a top view. And our coordinate system, our x-axis points towards our forward direction. So this would be our forward motion. So we consider this to be the front of the car. And then this would be our y-axis. And then, of course, right-hand rule, z would be out of the plane. And the way that they're numbered for our robot is wheel 1 is in the front left, wheel 2, 3, and 4. So then the question is, we know that these are omnidirectional wheels, and so we anticipate that this whole system, that we can move it omnidirectionally, which means that we can instantaneously rotate in any direction and translate in any direction. So then the question becomes, how do we actually achieve that when we have to control 4 different wheel velocities? So the first case that we'll look at, and so first I'll give you the more general idea, and then we'll look at the math as to why that actually works out the way it does. So let's say we want to move forward. So we want this whole thing to translate in the positive x direction. But we achieve that by moving all wheels forward. So if we resketch the robot here, so what happens when we apply a forward velocity to this wheel, we get a forward and right. When we apply to this wheel, we get a forward and left. And here we get a forward left, should be 3, 2, and here we get a forward right. And so what we have is if V1, V2, V3, and V4 are all equal, so this is assuming that all of the wheels are the same, so they have the same radius. So if we apply the same velocity to each wheel, then, so this is our x, and this is our y. The y-axis components cancel to give pure forward motion. Right. So you can see here that V1 and V3, V1 has a contribution in the right direction, V3 has it in the left direction. If these velocities are equal, since the angles are equal, then those two would cancel each other out, and then you just have those forward components. Similarly for the back wheels. And so, like the forward, you can move backward simply by moving all wheels backward. At the same speed. So if we're going backward, this wheel moves back and left. This one moves back and right, back and right, back and left. And so again, you can see that we have contributions in the y directions, which will cancel out. So we would get a purely backwards motion. So now let's say that we want to translate right. So this would be move in the negative ym direction. So in this case, what we want to do is the A wheels we move forward, and the B wheels move backward. So what does that look like? So these are the A wheels, and we're moving them forward. So we have V1 and V4 here. And then we're moving the B wheels backwards at V3 and V2. And so if our magnitudes of V1, V2, V3, and V4 are equal, then our x-axis components cancel, to give pure right translation. So same kind of idea, we can see V1 and V2 have opposite contributions in the x. V3 and V4 have opposite contributions. So if we have these velocities equal, those x components cancel out, and then we just have all of these y components, which are going in the right direction. And so then, likewise, if we want to translate left, then we have A wheels backward and our B wheels forward. So same kind of idea as we had for translate right. Now these ones go back. And these ones go forward. And so we might also want to do rotations. So if we want to rotate right, so that would be rotate clockwise. So this would be like rotating about minus the z-axis. So to do this, we want the left wheels to go forward and the right wheels backward. So this is similar to what you would expect for a regular, like an Ackerman type car. But because we have the additional sliding, we're able to rotate directly about the center of our robot. So we have V1, V2, V3, and V4. And so because we don't have this, like the Ackermann style, we would have two velocities going in this direction, and these two wheels would be kind of dragging along. So we'd have rotation more about a center of rotation. But because of the nature of these wheels, we can actually instantaneously spin about the center of our robot. And similarly for rotating left, it's right wheels forward, and left wheels backward. So same kind of idea. Except now these are going backwards, and these ones are going forward. And so you can see by the direction of the velocity components that we'd be rotating in the counterclockwise direction. So these ones I'll do a little bit more compact because they're all very similar in idea. So if we want to move front and right, we move the A wheels forward and the B wheels are stopped. So basically we just let those roll freely. Is that blurry to all of you? Or is it? Okay, never mind. So in this case, our A wheels are going forward. And then the B wheels just have no applied velocity. So you can clearly see that we're going front right direction. Move front and left. Same kind of idea. B forward. A stopped. And then similar kind of idea if you want to move backwards. So if you wanted to move back left, then you would apply the backwards velocity to A. If you wanted to move back and right, then you would apply the backward velocities to B. And something cool you can also do, which is a little bit more complex, but you can also spin about a wheel axis midpoint. So let's say, for example, that we have a robot here. And let's say that I want to rotate right about the front axis. So this point here, I want to rotate right about that axis. So what you do is you look at how you rotated right for all four wheels. So here we had the left wheel's going forward, the right wheel's going backward. And so what I do is I apply those velocities only to those wheels that are not on the axis of interest. And so I let the front wheels have no applied velocity. I take the velocity for the other two wheels from the four-wheel case, and what I'll actually get is a rotation about this point. And likewise, if I wanted to rotate about the rear point, then I would apply the velocities to the front wheels. So use the rotation directions for the center rotation case. And we apply these directions to the wheels on the, as I'll say, the opposite axis. So not the axis where we want to rotate. And then the other wheels, we just leave stopped. So that gives us kind of a rough idea if we want to do these different motions as to how we might achieve those. But let's look at the mathematics here to explain this a little more clearly. And then that also allows us to do more complex motions as well. So I'll sketch a little bit bigger here. So I guess a quick, easy way for sketching these is you notice that all of the axes point towards the center of the robot. So this is wheel 1, 2, 3, and 4. We have our local coordinate frame for the robot. And so just some terminology, the distance from this wheel axis and this wheel axis is considered the wheel base. From the center of this wheel to the center of this wheel is known as the track. I'm going to label a couple of distances here. So half the track I'm going to call A, and half of the wheelbase I'm going to call B. And so I'm not going to go detail through the derivation, but I'm pulling from the paper, which I also included. I think I had the link in the syllabus, but it's also in the general resources in the box folder. So from kinematic model of a 4 mecanum wheel mobile robot by Tahin and G. might have copied his last name wrong. But if you look at this paper, there's a little bit more detail on the derivation. But the main idea is that when you're coming up with the kinematic equations, you take the constraint equations. So where we have the rolling and sliding constraints for the standard wheel, for the mecanum wheels, we only have the rolling constraint. Because of the rollers, we don't have that sliding constraint anymore. But you take those and you combine them, do some simplifications. Then we have the rotational velocities of each wheel. And note that our wheel number order is different for our model than what it was for the robot in the paper. So you'll notice that there is some difference in the two models, but the derivation is the same. And so R is the radius of the wheel. 1, 1, 1, minus 1, 1, 1, minus 1, minus A plus B, A plus B, A plus B. And then we have our cosine theta minus sine theta 0, S theta, C theta 0, 0, 0, 1. So these velocities are in the robot frame. And then this x dot, y dot, theta dot is relative to our inertia frame. So some fixed frame that we want to know our relative position to. And so that's why we have this additional rotation here, is to put this these coordinates that are in the world frame into the robot frame. And then you can invert this using a pseudo inverse, because this is a non-square matrix, to get x dot, y dot, theta dot is equal to r over 4, 1 minus 1 minus over a plus b, 1, 1 minus over a plus b, 1 over a plus b, minus 1, a plus b, okay, that's not right. It's an inverse. So that should have been here. Just a moment here. My apologies. And here should have been the inverse of this matrix. C theta, S theta, 0, minus S theta, C theta, 0, 0, 0, 1. All right, so we apply the pseudo inverse, bring this to that side, and then we invert the cosine, or the rotation matrix as well. And so when we do the inverse of this rotation matrix, basically it's like replacing theta with minus theta, and that's why we get the sign change here in the sine functions. And so the question is, does this align with what we were talking about in all of these cases as to what velocities we should apply when we want to move in certain directions? So let's say that theta equals 0. So our rotation here is just the identity matrix. So that simplifies things a little bit for us. And What that also means is that our xm and ym are aligned with our inertia x0 and y0. And so let's say that we want to move in the positive direction. So x dot positive, y dot, and theta dot 0. So if we were to plug in y dot theta dot is 0, and this is just the identity matrix now, what would this tell us about the applied wheel velocities? Well, what we get is x dot over r equals phi dot. So I'll just use phi dot to be an abbreviation of all four of the phi's. Just so we don't have to keep rewriting all of this. And so this is just what we had in the forward case, where we said if we want to move forward, we should move all of the wheels forward. So all of these phi's have the same sign as x. And this also tells us that all of the phi's should be equal. So the same thing that we said here, all of those velocities should be the same value so that the y-axis components cancel out. And then similarly, let's say that we want y dot positive and our x dot theta dot being 0, then what we would have is y dot over r. And so in this case, we'd be pulling off a -1, 1, 1, -1. We have -1, 1, 1, -1 equals phi dot. So what this tells us is wheels 1 and 4 move backward, 2 and 3 move forward. So 2 and 3 are moving in the same direction as y that we want, and 1 and 4 in the opposite. So a positive y would be a translation left. So we can see, just like this case here, we had 1 and 4 moving backwards, and 2 and 3 moving forwards. And then, as for completeness, we can also verify we want theta dot positive, so x dot, y dot 0. Then what we have is theta dot over r minus a plus b minus a plus b, a plus b, a plus b equals phi dot. So that means 1 and 2, we'd apply a backward velocity to, 3 and 4 would move forward. And so definitely anytime you get a model, you want to test multiple cases. So let's say theta was 90 degrees. So in this case, what we would have is our inertia frame, be something like this. And then our robot, we'd have xm rotated by 90 degrees. And so in this case, let's say then, right, so first we need to do the corrections. We have theta dot equals 1 over r, 1, 1, 1, 1, minus 1, 1, 1, minus 1. I'm just going to let S equal A plus B, just so I don't have to keep writing that. So we have minus S, I'm going to say T just because I used S for sine. And so now if we plug in 90 degrees to our rotation, then what we have is 0, minus 1, 0, 1, 0, 0, 0, 0, 1, x dot, y dot, theta dot, which is 1 over r, 1, 1, 1, 1, minus 1, 1, 1, minus 1, minus t, t, t. And so I'll just multiply this part out, and what we have is y dot minus x dot theta dot. And so then let's say that now we want y dot positive and x dot theta dot 0. Well, now this y translation in the inertia frame is actually an x translation in the robot frame. So this is translate forward in our robot frame. So what we have is phi dot equals 1 over r, y dot 1, 1, 1, 1. Right. And so same as what we had before, when we were moving forward in the robot frame, it was all wheels moving forward. And so we can see that this kinematic equation does take into account correctly the difference between the robot frame and our inertia frame. And so likewise, you can check for x dot being positive, theta dot being positive. And of course, what's nice is that the theta dot is always going to be consistent, right? Because the z-axes are parallel for those two. And so when we're talking about kinematics of mobile robots, there are a few other terms that are of interest to us. So one of these is maneuverability. So this describes basically how easy or hard it is to reach certain spaces in our robot workspace. So if we look at another term which you'll see in the book, is kinematic mobility. So this is the ability to directly move in the environment. And so what dictates how we can move in the environment is a combination of available mobility from our sliding constraints and additional freedom from our steerable wheels. So if you think about the case of an Ackerman type car, so a car like what everybody drives. And so in this type of car, what we have is we're going to assume it's a front wheel drive, so we can change the steering angle of the front wheels and the two back wheels are fixed. And so this is an Ackerman So we can control our applied velocity and our steering angle. And so what dictates how we can move is part of those sliding constraints. So what we know is that in our standard wheels, that we can't slide in the direction perpendicular to the wheel plane. The same is also true for these front wheels, these steering wheels, steerable wheels. And what we find when we trace these, what we call zero motion lines from our sliding constraints, what we get is that these meet at one point, which we call the ICR. So the ICR is our instantaneous center of rotation. And so this explains why when you're driving your car, you can't instantaneously move in any direction. Because of these sliding constraints, you can only, if you don't, so eventually you can change, right, as you keep changing your steering angle, but instantaneously your steering angle is fixed, right? And so when you apply the forward velocity, you actually are forced to move along this arc. So this circle that goes about this instantaneous center of rotation. And then of course, you can have it where it goes to the infinite case where you go in a straight line, right? But in general, you have a fixed arc that you're allowed to actually move along. And so this explains why we have a lower degree of mobility with this type of car. So in this case, we can only move along a circle for a fixed steering angle. So our degree of mobility is equal to 1. So you can get more detail of this in the Intro to Autonomous Mobile Robots book. In section 3.3, they go into a little bit more detail, and you can see a little bit better sketch of this ICR. And so this first was our degree of mobility. Like I said, it comes from the standard wheels where we have the sliding constraints. And so what we have is, as we have more constraints, it limits the directions that we can move in. And so the actual degree of mobility is defined as, for the mobile case, so in general, we can move in 3 directions. So we have x, y, theta. And then we subtract from it the number of independent constraints. And these constraints are from standard wheel sliding constraints. So our degree of mobility does not take into account the fact that we can steer these wheels. It just tells us what we can achieve purely through the applied velocity. Right? So movement achievable from from just the applied velocity. And so what we have for the Ackermann car is that we have two constraints. So we have this one constraint that comes from the rear wheels. So because these axes are aligned, there's actually a redundant constraint there. And these two front wheels are actually also coupled, so it's not an independent constraint from each other. So these two apply a single constraint. So we have two constraints total, one from the front wheels and one from the back wheels, which gives us an overall degree of mobility of 1. And the notation we use is delta little m. Now, for our robot that we're using, Rossmaster X3, so we have no fixed standard, so we have no standard wheels, they're all omnidirectional wheels. So we have is 3 minus 0 is 3. So we have full controllability of our space because of our omnidirectional wheels, and we only need to use velocities to achieve that. And then we also have the degree of steerability. And so for the Ackermann, we have delta S is 1 because these two wheels are coupled, or we control with the one steering angle. And then, of course, for our Rossmaster, as we have omnidirectional wheels, we don't have a controlled steering angle, so the delta S is 0. And so then, between these two, we get our overall degree of maneuverability. So delta capital M, which is equal to our degree of mobility plus our degree of steerability. So if we weren't able to steer our Ackermann car, then basically we'd only be able to move along a single arc or a single line by adding in a degree of steerability that increases our maneuverability some. So then for our Ackermann, what we have is delta M, 1 plus 1 is 2, and our Rossmaster is 3. So basically what this describes is the overall degrees of freedom that we can manipulate. And so this explains why when you're using your car and you want to, say, parallel park, that it's a little bit more difficult because you have less maneuverability than you do for an omnidirectional robot. And some other terminology that section of the book goes over is differentiable degrees of freedom. So basically this tells us the number of independent achievable velocities, and it is equal to our degree of mobility. So basically what this tells us is that for our omnidirectional robot, we had a degree of mobility of 3. So that means that we can independently control our x velocity, y velocity, and theta velocity. And so we can do any combination of those velocities that we want. For the Ackerman, we only had 1 degree of mobility, so that means that we can only control our velocity along one direction. And so the terminologies that I had before, holonomic and non-holonomic, we can actually relate these terms to this differentiable degrees of freedom. So for robot to be holonomic, the differentiable degrees of freedom is equal to the degrees of freedom of the workspace. And so our omnidirectional robot is holonomic because our workspace is 3 degrees of freedom and our differentiable degrees of freedom is also 3. And for the non-holonomic, those differentiable degrees of freedom is less than the degrees of freedom of the workspace. So basically, our non-holonomic condition comes from standard wheel constraints, as we had seen before. And so this is why controlling a Ackerman type robot is a little bit more difficult. So it comes down to a trade-off between the maneuverability and the stability. As we talked about before, if you have the Meccano type wheels and say you want to do a fast turn, you're going to get a lot more sliding than you are with an Ackerman type, and you're also going to have a lot more slippage. So estimating where you are based on odometry data alone is more difficult for an omnidirectional robot versus an Ackerman. So a little bit of trade-off depending on what emphasis you want to put on for whatever your application is. Right. And so I guess what we can say then is Ackerman are limited because our differentiable degrees of freedom is 1, and our Rossmaster X3 can follow any path in the workspace. And a definition thing that I want to clarify, because a lot of people use the two terms pretty interchangeably, but they do have an important distinction. So path versus trajectory. So if I have a point A here and a point B here, this then is my path, right? So this just tells me the positions in space. The trajectory is a path indexed with time. So, for example, I could start here and I could go fixed velocity along the path. So that's one type of trajectory. I could maybe go fast and then slow, fast, slow. And I'm still moving on the same path, but the trajectories are different. So that's an important distinction between those two terminologies, because the trajectory is what we're really going to be interested in when you look at the dynamics of a system. So you might be able to move along a certain path, but only if the velocity along the path is below a certain threshold if you want stability, right? So just a notation thing, because you will hear a lot of people use them interchangeably, but they do actually have a distinction between the two. And I'll just say a couple things about motion control. I won't get too much into detail here today, but motion control is basically you want to generate and follow a trajectory. And so, as you can imagine, for the non-holonomic type robots, this can actually be, especially the generate part, pretty difficult. And I'll show you an example of that in a moment. So the first type of control is open loop control. So if you took Robotics 1, you might be a little bit familiar with this term. So the open loop, what we do is we pre-compute a trajectory. Then we use this to command the robot. So say we have some x dot, y dot, theta dot that we want to follow. We can use our kinematic equation to figure out the phi dots for each of the wheels. Or if it's the case of the Ackermann, we can figure out the velocity v and the steering angle beta. And then what we would do is just at each time index, we would directly send that to the robot. So there's some potential problems with this. So this can be difficult to pre-compute, and it does not address dynamic environment changes. So if you just do open loop control, you just send the commands, and it doesn't matter if stuff moves around in your environment, or if you start accumulating error in your wheels, you don't take that into account with the open loop control. As to why it could be difficult to pre-compute, if you think of, for example, a dreaded part of every driving test. So let's say that these two front wheels are the ones that you can rotate, and the objective is to translate right. And so figuring out how do you actually achieve that. So through experience, we know that you can go forward and then you can go backwards. Maybe not the best sketch. And you can, through multiple maneuvers, you can get to this position, but it's not entirely intuitive how you actually get there, because you have to always move along either a straight line or an arc, right? So you have some kind of arc movement at the beginning, and then you have an arc backwards, and then you move again in those arcs to get to those positions. And so actually figuring out a priori what that looks like can be very difficult for these type of systems. So what we might do is some kind of feedback control. So I added a paper which is a summary of different types of control for mobile robots, and also has links to those papers as well. So different types of feedback control is a wealth of literature, and especially for mobile robots that have been used for decades. There's a lot of different ways that you can do the control. I'll just present the simplest form, which is like a PID type. So if you can, I'll do the definition first. So if this is our control input U out of the PID, so by our PID, we have our proportional gain, which looks at just the error at that time instance. We have our integral gain, which looks at all of the past, this should be like I maybe, all of the past errors and accumulates those. And then we can also have a derivative, which is looking at the change in the error. So it's almost like a predictive term and tries to compensate for what it thinks the change in the error will be the next time. So if you're not familiar with PID, definitely let me know and we can discuss in a little more detail. You'll see PIDs a lot for like motor controllers, for example, in a lot of industrial cases. So it's still used a lot despite its simplicity. And so you might have something like, say you want to move to some position, x, y, theta, or some pose, x, y, theta. So you could figure out the velocity that you need by looking at, say, where you want to be, so your x desired. And let's assume that you can somehow measure your x position relative to your fixed frame, and then you would have some kind of gain here. So this would be just a simple proportional type that you might use to drive your robot to some desired pose. So, of course, the big question is, how do you actually get this x, y, theta? And so, in a few classes, we'll be talking about ways that you can localize your robot. So figure out where your relative position is to some fixed point. And so typically we use a lot of sensors to achieve this, because our odometry can only get us so far because of things that we talked about before, like the slippage of the wheels, changes in the environment, and so on. So what we'll be talking about a little bit more next class, I'll kind of give you a preview. So next class we'll be talking about ROS, which stands for the Robot Operating System, which is a little bit of a misnomer. It is not a true operating system. It is what is sometimes referred to as a meta operating system. So it's not like Windows or Linux, typical ones we think of for operating systems, but it does do some of the similar functionality. So actually, since ROS first started, I think in 2007, the number of robots and sensors that use ROS has actually grown exponentially. And a lot of industries are starting to use ROS as well. It's used a lot in academia. They're actually looking at developing a space ROS for space applications. So one of the things that is currently a concern for the original ROS the security was not the best. So they're trying to fix that some with ROS 2. And of course, Space ROS, that's one of their big concerns, is how to make sure the security is at the level that they need it at. But the main idea is that with ROS, you can basically upload, you can create packages that contain code so that we don't have to keep rewriting this code, right? So it used to be if somebody got a like a ROS master in the lab here, you write up the code to be able to interface with it, and then somebody got the ROS master, say in UC Berkeley, and they write the code to interface with it, and this is just a lot of wasted time. So if we already wrote the code, why is UC Berkeley writing the code? And so that's what ROS really wanted to solve that problem, is how can we make this code open source and available to everyone, so we're not wasting time implementing these things, that these algorithms that a lot of people are using, or these interfaces that a lot of people want to use. And so we'll dig into that a little bit next time as to what ROS is, some of the things that we can do with it, and some of the layout of ROS. So has everybody kind of started on mini project 1? Okay. So any problems so far? Yeah.
So on task 2, where we have to connect to the ROS master with our phones, I'm having trouble actually getting to that.
Okay.
I've gotten to the point where, basically when I start up the robot, I get the IP, and then I put it in the app on the phone and connect it to the Wi-Fi, and then it just like stays.
So you're connected to the hotspot?
Yeah.
Okay. When you start up the robot, you can see on the screen where it'll say version.
I don't remember.
If you see, so I guess this is a general thing. If you see version and it says -1, then that just means something didn't boot up right, and so you just have to restart it. And sometimes it takes a couple restarts.
Okay.
So you should see something like version 2.3, I think they should say.
I tested it on 2 robots just because I wasn't sure, and both were unresponsive from the app. I don't remember seeing the version though.
And
okay.
Yeah. Do you have an Apple by chance, or is it an Android? Okay. Because I know Apple's computers, and that can sometimes be a little bit of an issue. Yeah. So it's definitely, if the version comes up -1, that's an issue we've seen. Yeah. And I have another class after this one, but I get done at 2 as well. So if you're still having problems, then let me know. I can stop by. Any other issues so far? It seems to be more user friendly than the ARM. About the same so far. All right. So hopefully, I know with the ARMs we had a couple of them that didn't quite make it through the semester. I'm hoping that we can get all. Well, currently we have 5, but hopefully we can get them all through to the end of the semester. But I'm hoping, especially for your final project, that you'll be able to do some coordinated motion with multiple robots. So hopefully that should be good. I also wanted to check what you guys see in so when you guys log into Box, I just want to make sure that, can you guys actually see all of the subfolders when you log into, so on Piazza, I had, so under general resources, I have reading resources, which should take you to this general resources folder. And so this has a lot of additional reading material, and I have it divided up a little bit based on the topic. I haven't shared a lot with Box, so I don't know if by sharing the top level box folder, if you guys have access to all the subfolders. So if you can't access anything, please let me know and I'll just set up additional links or see what I need to do. But each of these I tried to populate. So for example, Ross has some different Ross slides to give you a little bit more detail as we're talking about it. Similarly, I have all of the books that I talk about. So especially these Chaucet and this Intro to Autonomous Mobile Robots. I have the links to these also in the syllabus, or you can just download all the books to start with. And I do try and put in the syllabus what section I'm actually looking at, so you don't have to try and figure it out for yourself. But if there's any problems with accessing or downloading any of this information, please let me know. There's definitely a lot of stuff to cover and not a lot of time. So this gives you a chance to look also at some beyond things. So for example, in kinematics, there's this steering theory. So you can actually look at expanding onto the dynamics and how that affects your ability to steer. So a lot of math, but there's some interesting ideas in here as to how you can maintain stability when you account for the dynamics when you're steering. So a lot of additional information. Hopefully it's relatively easy to understand what's where. If anybody has any suggestions as far as how things are presented, then please let me know, because I know there's a lot of material also through here. But I've definitely been trying to use the syllabus to hopefully guide you a little bit into those resources. So are there any questions, any other pending problems, concerns, feedback over course structure so far? All right. So have a good day.